In this lecture, we're going to look at the stability of transition metal complexes, and then we're going to focus on the applications of coordination compounds. Specifically, we will talk about biochemical applications. The reading you need to do for this includes section 6.2, 6, and 6.5 in your textbook, and there will be some handouts on rubidoxins and ferredoxins that you want to look at, and also nitrogenase. Now, we finished up an extensive amount of information on coordination compounds. There's actually two key points that you need to understand to know about the stability of transition metal coordination compounds. The two things are hard-soft acid-base theory and the chelate effect. Hard-soft acid-base theory is very simple, and you can use the periodic table to understand it. Hard and soft refers to the polarizability of ions. Hard ions are small ions or molecules with very few electrons. Since it has fewer electrons, it is not as polarizable. Soft, anything that is classified as soft is a large ion or molecule with many electrons. Hard and soft will be applied to the Lewis concept of acids and bases. Remember that a Lewis base is an electron pair donor and a Lewis acid is an electron pair acceptor. Hard-soft acid-base can be used to explain different chemical trends, specifically why certain transition metal cations react strongly with certain ligands. So let's define hard and soft acids and bases. Hard acids are small, highly charged metal cations with a low polarizability, like Fe3+, CO3+, and Cr3+. They're found higher up in the periodic table, and they generally have fairly high charges. Hard bases are small, highly electronegative ions or ligands containing donor atoms with a low polarizability. So ligands that can include this are F- and ligands containing nitrogen and oxygen atoms. Soft acids are large cations with small charges. Soft acid cations have many electrons and are very polarizable. And the examples that you can think about are Pt2+, Ag+, and Au+. Soft bases, they are large and they have lower they're lower electronegative anions or ligands with a donor atom that has a high polarizability. Some examples of this include I- as a ligand and ligands containing C, P, or S. Now, if you look at the periodic table, you can rationalize a couple trends. As you have more electrons, you're going to have a smaller effective nuclear charge on the outer electrons, and the polarizability of that ion will increase. So as you go down the table, softness increases. Also, as you go from left to right across the periodic table, softness will increase as well. The third criteria that will lead to increase in the softness of a Lewis acid or base is decreasing charge. So you would expect Fe2+ to be softer than Fe3+. I would strongly suggest, if you want to learn even more about hard-soft acid-base chemistry, and this is actually a very good site. Go to the website at the bottom of this slide. So let's think about how to use the hard-soft acid-base principle. Experimentally, hard acids prefer to react with hard bases, and soft acids prefer to react with soft bases. So for example, Ni reacts with 4 COs to form NiCO4. It's a soft acid plus a soft base leads to a stable compound. The same goes for this. Even though CO is bonded to 6 H2Os, the CO is CO3+, highly charged, not too many electrons, making it a hard acid. It will react with 6 NH3s, which NH3, since it has a nitrogen in it, that's a hard base. And you end up getting a stable compound, CONH363+, and the 6 waters dissociate. Now this isn't always the case. Think about this compound for a minute, AgNH321+. Ag1+ is a very large cation and it has a very low charge, making it soft. NH3 is a hard base with nitrogen bonding to the Ag. This compound is well known and forms readily when you put aqueous ammonia in with silver. The hard-soft acid-base principle is just a guideline to help you think about what would help a stable compound form. Here's the easy way to rationalize the hard-soft acid-base principle. Hard-hard interactions, that means a hard acid reacting with a hard base, the bonds that form there are only sigma bonds. You don't see too many pi bonds or pi back bonds form. So the sigma bonds are very strong. When you have a soft-soft interaction, that's a soft acid reacting with a soft base, the stability of that bond and that compound comes from the fact that pi bonds and pi back bonds can form. So that's it for the hard-soft acid-base principle. It's very important and you will use it quite a bit when you think about the homework problems that I will post for this section. Now let's start talking about the chelate effect. This is an effect that happens when you have a cation that's surrounded by monodentate ligands. And the cation has all of its monodentate ligands replaced by multidentate ligands, such as ethylene diamine or EDTA. Now, what we're looking at here is the compound, and we're going to change out all of these monodentate NH3 ligands for EN ligands. And we're also looking at the log of the formation constant. Notice that when you go from copper NH3 2+, to copper En 2+, that means the 4 NH3s are being replaced by 2 ethylene diamines, you have a significant increase in the log of the formation constant. The same goes for when looking at nickel NH362+, and replacing all the NH3s with En. You have a significant increase in the formation constant. So the question is, why?